Okay, I am Santosh. I've done my PhD in something called as biomicro manipulation, and it is to establish mechanical properties as a biomarker. Just to give a perspective, before going too much into technical stuff, which I don't believe in to begin with, one of the things that we used to practice in our lab very judiciously is first is know the audience who you are talking to, and then always have a big picture of what you're doing rather than going into the specifics, because there are very few people, especially people, are you all from the research background? There will be very few people in the world who will be able to understand when you present the specifics of your subject. So keep the thing as big a picture as possible and get into the specifics whenever a question or a two arises on that particular thing. So my work was mostly on as I said, mechanical properties of biological cells and tissues. Just to give an example, how do you buy a vegetable? What do you do when you want to buy a vegetable? Okay, what else? Say mango. Usually you palpate a mango to see if it is ripened or not. Or if you're buying an okra, lady's finger, you usually bend and break it. If it breaks, it's good. Otherwise, it's not good. So inherently, even if you go to a doctor, he or she puts hand on the abdomen and tries to palpate to see if something is wrong. So intuitively we have a point where I can discern your health condition based on some mechanical response that's coming in. Now, if we were to extrapolate this idea to a place where something like a cell or a tissue, can I build devices or tools that can help me do this, is what was my thesis all about. But in the specific nature of my thesis, I worked on something called as a compliant mechanism. I'll pass around this particular thing. So the idea of a compliant mechanism is, okay, I'll just finish this and review. So what you see over here, what I want you to observe is you have a scissoring action, but there are no joints. If you would have observed any scissor, it will have multiple components to it. There will be one piece, two piece, and then a rivet. That's what will give the thing. This one won't have any joints. So a compliant mechanism won't have any joints. It's purely based on the geometry and the material property of this particular geometry, which is giving rise to what we call a compliant mechanism. One of the attributes of this compliant mechanism is this particular thing is actually not a scissor. It's a holder to hold glass micropipettes or glass Petri plates. As you see here, it's holding my finger because its objective is to hold an object, but under no condition this will be able to damage my finger, because the way I have tried to design this is it will not apply any more load than what is necessary to hold it. So if you were to cut something, you might need a lot more force than what is needed to hold it. And that's how this thing has been tuned around. So I just pass this thing around, you can have a feel for it. Now, coming to this particular point, why it is important to have this perspective, the compliant mechanism perspective, when we are talking about mechanical properties, is that since the samples that we are using is of very small size, we want to develop or have tools that can go at that level and measure something. When you are talking about things at that level, one of the things that would be very detrimental is the assembly process. So if I were to build a scissor-like mechanism, just coming back to the scissor-like mechanism, at a micro scale, I might have to make these two discrete parts, and I should have an assembly process to put these things in place, which is very. How many of you have done MEMS fabrication? Have you read about MEMS? MEMS fabrication. Have you done MEMS fabrication? You should try once. It's an art. It's like cooking. It's an art. Not many people will get it, and it is very difficult, and you need to follow every damn step that is out there in the fabrication. Otherwise, it's very difficult for somebody to get going with their device. So coming back to the point of why compliant mechanism suits that particular thing, as you would see, you don't need to have any joints to create a functionality. Now, when I have eliminated the point of no joints, I have also eliminated the point that it doesn't need any assembly. So the whole point is, because there is no assembly, I can now design things at a very small scale, and when I design things at small scale, I can find or measure mechanical properties of different specimens. So through my thesis, we had scaled anywhere between very soft things like cells. So any idea like what I mean by soft? Because we generally don't use the word soft. Anybody from the bio background, biology background, 11th, 12th bio? Some of you. Okay. Since during my PhD, okay, I did my PhD 5 years back. So when we were reading the papers, usually whenever we read a paper coming from the bio background, they will mix these two terms, stiffness and softness. They will mean softness, or rather, they will mean low stiffness, but they will use the word soft. And something which is very high stiffness, they will use the word rigid. As engineers, it's difficult for us to digest these two terms because we are very sensitive to these terms. But in the spirit of it, if you look at it, because I cannot go and try to teach a biologist, no, what you are doing is wrong. That is offending and it is hurting their ego, because that's not the point that they are trying to reach. What they are trying to say is some physical property has changed, is what the spirit of the whole thing. So going by that kind of a spirit, there is always this sense of softness and low stiffness coming from the biology aspect of it also. So going back to my point, that any idea how soft the cell is? Any numbers? Any idea what is the Young's modulus of steel? 210 gigapascals. Okay. Any idea what is the Young's modulus of silicon? GPa. That is slightly less stiffer than steel. Any idea what is the Young's modulus of a polymer rubber? Approximately. Order. It's in megapascal. Yeah. Right. So it's in megapascals. Something is in gigapascals. This is in megapascals. Cells will be in the order of kilopascals. So giga, mega, and then this is in kilopascal. So it's very of low Young's modulus, very soft, low stiffness. The other extreme that we try to do is a miniature specimen of concrete. Now, why concrete we wanted to study is that when they build large structures, they have to do testing of those boulders in a specific manner to ascertain whether the composition of cement, sand and water can withstand the load that is coming out. It's a very essential thing in civil engineering practice. They need to get the right combination of sand, cement and water to achieve a particular strength of that material. Now, for them to test this large boulders, it was a pain. First of all, they have to make such a large boulder, then they have to carry it to the specific spot where they can do these kind of tests, and they have to test it. So that's where we were approached by the civil engineering department professor in asking us if they can make specimen of a smaller size, can we test it? And we were able to make these compliant mechanisms break concrete specimen. So the point that I am trying to drive here is, it is all about the problem statement that we are dealing with, not about how you want to approach the problem. So even in a very fundamental aspect of the research, which is applicable to all of you, is that first, you be strong in what you are doing, and the problem statement, you try to understand the problem statement and be very positive about applying your approach to addressing that problem. So that's what we are trying to do here also. Compliant mechanism. Since we know that compliant mechanism, as I was showing, it can apply only limited amount of load, that only means I can control the load. That is the objective. So when I can control the load, I can make it very soft or I can make it very hard. When I make it very hard, I can break concrete. When I make it very soft, I can hold biological cells. So we have tried to get that spectra of materials or the testing samples where we can utilize these compliant mechanisms in testing those things. Any questions? So I'm just pushing you with a lot of information. Okay, I'll just play you a quick video of what has happened after my PhD. This is mostly about the PhD work. But there are two things that was interesting during what I learned from my PhD, which I think is general, applicable even afterwards. I have my own startup now, and it is mostly on developing compliant mechanisms for a variety of applications. Right now we are building a device for what they call as test tube babies, in vitro fertilization, where I will show you as I play the video, you will understand why this particular problem statement was chosen. Okay, so even before this, there are 2 points that I wanted to emphasize. One is when I use the word manipulation, I was asked, how can you manipulate something? Because manipulation has a very negative connotation. They thought I am manipulating the data. Nowadays all this Cambridge Analytica, all these things. So the word manipulation in our terms means I can hold, squeeze, do a lot of these different kind of things which I will be showing now. So that is one point of clarity. And I do believe that it doesn't help anybody in manipulating the data. So let us be true in whatever experiment we do. Then the other thing which drove me to having this kind of a company, and even in terms of the career after the research. So most often people, I think you will also be facing this. When I say I am doing my PhD, they think I will become a professor. It's a societal norm that anybody who is doing PhD will become a professor. But my advisor, my Professor Anand Suresh, had a different perspective of why somebody is doing a PhD and who should be doing a PhD. So he used to call something called as K-acid test. So it is K-acid test, if I were to use the word. So K is knowledge. Knowledge is very external, in the sense you are not born with knowledge. Knowledge is coming on to you. So what he believes is, even if somebody doesn't have enough knowledge, they can always be taught upon. So in that way, knowledge is an external thing, it is an hyphenated one. Then comes acid. The full form of acid that he has is, first is attitude. You should have the attitude. Then comes curiosity. You should be very curious about what you are doing. I stands for imagination. You should be able to imagine. I think power of imagination gives you to do a lot of experiments, even otherwise you want to do it in physical world. In a virtual world, you can actually build your experiment completely, so that when you do the experiment physically, you are kind of planned out everything. So that is the power of imagination. So imagination is very important. And what is more important than all the three things is diligence. You should be really sincere to what you are doing, and that takes you places. So he believed in this K-acid test. So when I was in the juncture of finishing my PhD, and I had a sense of starting the startup also, but that's where any career that you're going to build after PhD, you should be able to, because we are the people who are in the research who have cleared this K-acid test. In some sense, we have acquired the knowledge, we have the right attitude for research, then we are very curious to know new things, and we have good amount of imagination. That's how we have built the research, and we have been diligent. That's how we have been able to put in a lot of work. So we are the people who have passed this K-acid test when we call ourselves as researchers. So given this kind of a spirit of the K-acid test, it is not necessary. If you want to become a professor, you will have all those characteristics, suits. But all these characteristics also suits for an entrepreneur. Entrepreneur needs to know a lot of things, needs to be curious, needs to have an open mind, needs to put in a lot of effort. So that's where I thought, okay, it still fits on to what I have already done. So that's how we try to build our career opportunities, even as we did with the what we thought beyond the PhD work. So this video gives you a sense of what we try to derive upon the PhD work that was already being done.
Palpation is one of the oldest techniques that doctors still use to discern their patient's condition. Can you palpate a single biological cell to discern more? Our microscale grippers can. Using a novel design paradigm called compliant mechanisms, we at BenFlex R&D are developing microscale grippers that not just hold the biological cells that are about 10 microns in size, but can do things like palpate, inject, stretch, probe, etc. Cell gripping technology is particularly useful when you have limited test samples. For example, in case of in vitro fertilization, if you have to choose the right ovum to inject the right sperm, you cannot put these resources through any chemical test because they are all invasive and will make it unusable. In such cases, our non-invasive gripping technology comes to rescue. It can help doctors distinguish between the healthy ones and unhealthy ones. Single-cell gripping manipulation can become a biomarker as opposed to existing biochemical assays. However, they can coexist too. This makes the diagnostics more effective than ever before. At BenFlex R&D, we believe mechanical biomarkers are the next big thing in medical diagnostics. We are geared towards it. Support our initiative at www.benflex.in.
So BenFlex is my company. Name BenFlex, you might have guessed by now, but it's all about bending and flexing. Compliant mechanism is all about bending and flexing. And there are a host of things that we can do with compliant mechanisms per se. I'll just play the other videos before doing this. Okay, thanks for coming. What did you do? Let's play some videos which were part of different kind of testing that we have done on samples. This is a cancer cell. It's called MCF7, Michigan Cancer Foundation 7. So what we are trying to do is you have two arms of the gripper, the micro gripper, coming and holding onto a cell. So when I apply a little more deformation, I'll be able to squeeze it. When I squeeze it, I can tell the mechanical properties. So, any idea what is the size that we are talking about? Sorry? Nano? Oh, okay. Sorry? Oh, no. Oh, sorry. No. Yeah, I mean, it's very low. Definitely. This is about 10 micron. The circle that we are seeing is about 10 micron. And the overall mechanism that you are seeing is about 5 micron. So that's the scale that we are talking about. We're talking about cell manipulation. So in this video we are handling what we call as Drosophila embryos. They are embryos of Drosophila. You understand the word Drosophila? Drosophila is fruit fly. What you see in all your fruits. It's an ink of the Drosophila. And what we are trying to do is once again squeeze. And in this particular scenario, they also do Drosophila is a good sample for people who are into genetics. So they have to hold this Drosophila embryo and induce some kind of a genetic modifying material. For them to hold the Drosophila embryo is not trivial. In the sense, they have tried to do a lot of things. They even put things like gluing, where it can just not move when they are doing the injection. So we kind of develop these small scale pupils which can just go and hold the Drosophila embryo when you are doing the injection of the other cell. This is typically a compliant mechanism gripper when I show. This is how it is. In the sense, there is an input, then there is an output, and a lot of things bend together to get to do a certain kind of functionality. And what we do in this particular thing is we choose the material because material plays a very important role. But it is still material agnostic in the sense. We have done, so when you talk about bending, usually things which are brittle in nature, you will think that it is not a good candidate for this mechanism. But that's not the case, because we have also built things with silicon. Silicon, which is supposed to be brittle, as long as things can bend or the deflection is there, the things can work for us. So it is material agnostic. The other aspect to our compliant mechanism is the geometry in itself. How do I choose the dimensions? In the sense, length of the beam, width, in plane, out of plane thickness, all these kind of geometric parameters get into the design, and that's how we design this compliant mechanism. Then there are various approaches with which you can design a compliant mechanism. So this is a cement sample that I was talking about. It's a small 10 mm cement sample.
This is 20%.
So it's a complex mechanism. What you see over there, but it is now breaking a cement sample. So that's how vast it can be in terms of the stiffness that you can handle. Okay, this is an interesting experiment. We wanted to build a surgical tool where if a doctor is using that tool for operation, they should be able to cut muscles, but under no condition. That means if the doctor by mistake over actuates the system or does anything, under no condition it should harm the bone. So usually, have you heard of this Da Vinci robot? It's a mechanized robot which does the surgery, and the doctor will be in the console. That means he'll be given a joystick kind of thing, and he'll be moving around the joystick, and this will be doing all the things that the doctor should be doing. Now, what happens in such a system is that things are very stiff, in the sense it is not going to see whether something is soft or hard. As long as you move the joystick, it will go and cut. So there is a very high chance that the doctor by mistake over applies the joystick. When it is cutting your finger like this, it can also run into your bone and cut the bone also. Because it is not distinguishing unless there is no feedback in that, first of all. And on top of it, it has such a high stiffness that it can actually go through and penetrate into the system. So that's why we try to build a system where it will not cut when it meets the bone, but it cuts when it meets the flesh, the muscle part. So I'll just play this video. So what you see over there is a scalpel blade attached to a compliant mechanism, and we are just running that scalpel blade, and what you see as a more translucent material on the left side is a soft material. It's called a hydrogel. It's soft, it resembles muscle tissue, and what you see on the whitish portion is a hardened PDMS, which is a little hard, and it resembles mostly the bone component of it. In fact, bones are a little stiffer than that white. So I'm just moving the scalpel blade. So this is attached to one manipulator which just moves in the horizontal direction. When it is moving, so when it meets the harder portion, it is not able to cut, but it just goes above. It just scratches through it, it doesn't harm it. Then once it meets the muscle piece, it starts cutting. That means that the force that the scalpel blade is putting onto the specimen is now tuned in something like it can always cut something soft, and something is hard, it will never cut. This is a case where we are holding a zebrafish embryo. This is about 500 micron in actually. The idea here is something what I was showing with the blue scissor. I have to hold it in place, but under no condition I should be squeezing it. So I'll just play the video once again. So you will see that the mechanism is trying to do something around it, but it is holding it, but under no condition it is squeezing it. because that's how we have designed this. So this is a case where we had also coupled it with a haptic device. You're aware of what a haptic device is? You understand graphics, right? What does graphics do? So if you were to capture if you want to tell someone what graphics does, it's mostly enhances your vision. So whatever graphics is for vision, haptics is for sense of touch. In the sense, I am doing something remotely, can I get still the same sense of touch sitting out here using a system? So what we try to do here is a compliant mechanism. I'll come it's little detail in the sense that compliant mechanisms can also be used for force computation. Just to give an example, if I were to say this is my plate, and I'm applying a load, and you can see this bending happening. Now, if I know the bending, can I tell what was the force that went in? So, can I say that this thing can also be used as a force sensor? Because as long as I measure the displacement, the bending, it can also tell me the force. We are hitting upon a challenge that how unique is that? In the sense, I can apply here or here, the bending might be the same. But to a large extent, I can measure the force when I see the bending. So something of that nature, we try to do it in compliant mechanism. When I am seeing the displacements, I can also tell what forces went into the displacements. So what I need to do is, as long as I can capture images of the compliant mechanism, I can measure what is the force that went into the compliant mechanism, or the other way around, I can use compliant mechanism as force sensors. So going by this kind of a nature of compliant mechanism, what we try to build here is a haptic system where the displacements are coming as a console. In the sense, some joystick is given to the user. In the joystick, the user moves. When the user moves the joystick, it does something to the compliant mechanism. It either moves the compliant mechanism or actuates the compliant mechanism. And when he or she does this, and when it measures the force that's coming onto it, in an amplified manner, it is given to the user. That means, in this particular experiment, there is a small cell that we are holding and injecting. This is what we do in what I call as test tube babies, the in vitro fertilization. I need to hold the egg in place and inject sperms into it for the embryo to form and other things. So, given this kind of a scenario, when I am holding the cell, can I give the user the feel of holding it? Right now there is no feel because everything is done with a joystick and it just moves. You are only getting a visual feedback. Now can I enhance it to the actual feedback of the senses? That's where haptic device plays a major role. In this particular experiment, what we have done also is that the needle that you see over the other side, which you will be seeing once I play the complete video, this side, that's also connected to another compliant mechanism. So, as a user, now I am getting a feel of holding the specimen in place and also injecting it. It's exactly the feel that you get as a doctor when you are giving an injection to the patient. You should have that sense of injection. So that's the whole idea of this particular experiment. I'll just play the video. And so you see that the injection is coming. It's piercing through the object and taken out, and the object moves out of the system. So in all this, as a user, using the haptic system, I'm getting a feedback as if I'm holding the sample in place and also injecting in an amplified way. This just gives an idea of what we tell when we say of haptic system.
Here, you can see that the tissue-like material is held by compliant grasper and is touched using a scalpel fixed to the compliant force sensor called torque. Movement of the black region indicates the force detection. Here, user is using the phantom device to guide the
That's the
stabber
haptic device.
by holding the stylus close to the screen.
So when I'm moving it, it also moves the blade. And when I'm moving it, when the blade is cutting it, as a user I also get the feel of cutting something. Because it's giving that resistance force through the stylus. That's how the haptic system works. So I think I'll keep going on and on in terms of the research. I think that's one thing which we need to hold on. We get so excited about talking about our own stuff that we keep talking about. You want to? Can we make it a little more interactive? You had some questions you can take in or some kind of things.
Actually, the one which is near the cell, something what are holding or what would be the value?
Okay, that is a interesting question, and it also has an implication of how much is the cutting force that's coming onto it. So in this particular case, the notch radius, what we call it, was 1 mm. So it's scalpel blade. Sorry? This is a normal scalpel blade. I don't know the exact material. It should be of some steel variant. The blade. You are asking about the blade?
The one which was holding the cell part.
Oh, the holding the cell. Okay. Okay. Anything related to combat mechanism I have complete control. So that particular gripper was made of what we call as polydimethyl siloxane. It's a polymer which comes as two things. One is an elastomer, the other one is a hardener. So when you mix certain proportion of hardener into the polymer, it hardens itself. The overall dimension of that particular mechanism was about 8 mm. And the jaw distance was about 500 mm, because that's the specimen that we have put. So it also brings to a point where I was in my 5th year of PhD, and my prof called suddenly in July. He said, "You start writing thesis." We had never thought about it even a day before. I'm just coming to the end of my talk. That's why I'm making this point. Because you will never know when to stop, especially when you're doing research. You're so excited and engrossed into it. That's where advisor actually is important to tell that enough of doing things. So one of the things which he made a point is that even if we had given me another 5 more years of PhD, would we keep working? But what additional value it would have brought in? Definitely yes. Definitely yes in terms of the experiments that have been done. But in terms of the overall objective of the PhD, if it is achieved, you stop there. And get out of PhD and you continue with your research. I think that's a piece of advice that I will have with all, share with all of you. Because research is very engrossing. And it is like you are addicted to it. So even in the addiction, you should not miss out on some kind of milestones. So that's where it has taught me as an entrepreneur. It's very important to have an objective. What is more important is the milestones in achieving the objective. If you don't have the right milestones and if you don't realize those milestones, it's very difficult to see where you are headed. And you should always, it is always good to have a closure, then once again move on. So that's why you have all postdoc fellowship and all these things, which keeps you engaged in the research, but something has to be brought to an end. And that's how probably all the PhDs end that way, whether it is happy PhD or difficult PhD. At the end of the day, somebody says enough of things, you submit them. So I'll leave it with that message. If you have any questions, I can take it, and probably we'll proceed with the other things. Concrete is another application that I saw. Actually, my professor is the second generation of this company. His prof is referred as the father of computer mechanics. They are actually building even airplane wings using compliant. There is something called as Texas. It's an American company which is building compliant mechanism based airfoil. So one of the things that we were also working on as a project is that So airfoil needs to give a small amount of angle at the tailing edge for it to have that lift and drag. Now right now it is a two-part mechanism. That means there is one hinge sitting there, a lot of forces going on in doing this. So one of the things that is very crucial there is they need to add a lot of skin around it so that the airflow is not disturbed. Otherwise any linkage here, and if it bends, this portion here affects the overall aerodynamics of the flight. Now with the compliant mechanism kind of an approach, you don't need to have any hinges. So what you could do is something what is there in your body kind of, where you can gradually bend the airfoil. And when you do that kind of a gradual bending, the aerodynamics is even better. So around this particular concept, they have floated a company, it's called Lexus, which are bringing these, and it is in the testing phase. So, should I end? Should I continue? I don't know. Anybody working on virus? Interdisciplinary? I think we should try something interdisciplinary, because I feel most of the concepts in our own engineering disciplines are beaten off. Whatever we do, it's definitely exciting for ourselves, but may not be exciting in terms of the overall value add that you are adding into the society. Well, I mean the domain. So, and what I felt as part of doing interdisciplinary research is that there's a lot of scope over there where they are even finding it difficult to understand the overall thing. And as engineers, the kind of the direction, the perspective with which we address the problems is significantly different from the way they look at the problems. That's when we can add a lot more value. For us, solving a problem is more important than anything else. That attitude they don't want to have. I mean, they don't have. They are tuned to understanding the problem. So they understand the problem very well, they don't solve the problem. And we solve the problem very well even without understanding many times. It's okay for us. It's okay for us not to understand the problem, still solve the problem, as long as it is solving. That's the engineering process. So there is a lot of synergy in this approach, because there is a huge community out there who understands the problem in and out, but no solution. And we are good at giving solutions. So I think there is a lot of scope for interdisciplinary research. If you want to take any topics in bio, that's how we are all kind of motivated in trying to do something in the medical field or the bio field, because we see that okay, there is a lot of opportunity where I can be rooted in what I am doing, at the same time reach out to their problems.
Other than bio and concrete, is there any other window where we can apply this mechanism?
Compliant mechanisms?
Yeah.
That's what I said about the aerodynamics.
I didn't understand the scope. As far as cell is concerned, it's okay. But it can give me some wider scope of this mechanism to be better to understand.
Right. So one thing is the aerodynamics foil that I was talking about, which is a very commercial and large scale application of a compliant mechanism. Where do you see hinges? I'll turn around the question this way. Wherever you see linkages, compliant mechanism can be used. To give an example, one other place where we have used this compliant mechanism design, and it happened within our own lab. You know the stripping switches? When the voltage goes beyond trips. If you open the thing out, it's a large linkage that is sitting inside. That means there are a lot of mechanisms doing a lot of things for it to trip. Now your requirement, if you were to understand the problem state, is that when something goes to another state, it has to come down. That's your problem state, in a very bare minimum level. For this, they had used 22 components. Because something has to go up, when it goes up, something has to bring it down. When something brings the thing down, it has to go in some other direction. Lot of constraints. We got down the whole design into 2 components. So 22 components became 2 components using compliant mechanism design, which the company, it's actually in the commercial production now. Which company was, this company is Eaton. Eaton is one of the largest manufacturers of tripping switches. They are into commercial production. So the idea is, wherever there is rigid linkages, that means even the window, not a door is open, wherever there are hinges, it can be replaced with compliant mechanism. One thing which people usually doubt is the life cycle of this. You feel that rigid mechanisms can go for a longer number of cycles than a compliant mechanism because there is a failure in terms of material failure. But usually, anybody who is coming from a design perspective will tell that as long as you take care of the stresses that are coming into your design, means if you design well, it will last the cycles that is intended for. It means if you see that it should, for example, the tripping switch. The tripping switch should have a life cycle of 1 million. We have been able to do that. So it all depends on what kind of requirement you have in terms of the thing. We have even done things like double frequency. So just to give an example, you know accelerometers. Mobile phones have accelerometers. I'm just giving more applications of compliant mechanisms. So in our own lab, we had designed accelerometers. How will you make it more sensitive? Anybody from electronics background? Okay, great. So usually, why everyone chooses electronics-based solution than a mechanical or the physical-based solution is that we are not modular in our approach. If you really see the distinction in the approach of solving a problem, we are all first principles people. When you give a problem statement, you'll always try to think, do I know how the bending equation works? You'll start with the equation, then do it. If you really ask an electronics engineer, he will not solve the problem like this. He will say, I have one MOSFET, you will put this MOSFET, it will do that. It's like a black box kind of an approach. They know MOSFET, if you give an input, this is the output. As long as I put the MOSFET into this thing, it will work for me. Something like that. So, if you want to improve the sensitivity of an accelerometer, a lot of people in the world are using the electronics way of improving the sensitivity. One thing which we established and we showed through our papers also, is that the signal to noise ratio. So if you use an electronic amplifier to amplify the signal, is lot more. That means it creates lot more noise in the signal when you amplify using electronics than amplifying the signal using mechanics. A compliant mechanism, we also have something called as a displacement amplifier. That means if you give 1 unit of displacement, at some other point it will amplify it by 10 times, 50 times. So if I couple this displacement amplifier with my accelerometer, that lumped mass which moves, then I am amplifying the signal in a mechanical use. After the rest of it, once again it goes back in the electronics domain. But doing such an approach, we were able to not just improve the sensitivity of the accelerometer, but also create less noisy system. So there are various applications. Wherever you think of amplification of the signal or the rigid linkages have to replace by a compliant mechanism, it's always good. I try to emphasize on the things that I have worked on and what we are trying to do as a company. But the compliant mechanism in general has a lot of benefits. You can really beat it out. Yeah, fatigue failure is a part of the material aspect of it, and the stresses that go into your design. If you take this example of accelerometer, it has to go through a very high frequency operation. Even there it doesn't fail. Your compliant mechanism doesn't fail. In fact, you know how the accelerometer is done? Design of an accelerometer. Can I write? So you have a lump mass, then you have a spring. In a MEMS case, spring is never realized like this. It is like what they call as a folded beam structure. It won't be like our spring. And this mass moves based on your acceleration. When the mass moves, it finds some magnetic field, some electronic signal, and that's how acceleration is detected. For you to create this, it's a physical structure, it's a mechanical system. And if you realize that in the MEMS scale, it is like this. It's actually a compliant mechanism. It's a folded beam structure. Each one of them is a beam. And we are taking care of its mechanical properties even as we design. So, fatigue failure is definitely part of our design constraint, but it is taken care even as we design. airplane wing is massive. Isn't thing massive? So there are also things like we are trying to go this component mechanism route in terms of modeling, and then we hit upon this thing called as tensibility systems. So there's a lot of scope for us to expand the idea of component mechanism into different aspects of modeling in Excel. So yeah, the scope is immense, and also in terms of dimension there is no restriction. So in terms of design, there are various approaches for component mechanism. One of the approaches that we take, well, okay, even before one of the approaches, one thing is you can always stand by your intuition. You can intuitively design a component mechanism as long as you understand some amount of basics of how a beam bends and other things. So intuition is definitely there. But another approach that we use is what is called as topology optimization. So you understand the word topology optimization? Topology means network. This is how the points are connected. And optimization. That means in the cloud of points, how will you connect certain points in certain manner with certain dimensions so that it achieves our functionality. So when you have this kind of an approach, whatever you are telling comes as a constraint in my optimization scheme. So in that way, any solution space that I have would have taken care of the constraint that is coming in.
So is there any simulation kind of a thing justified at what the functionality?
Absolutely. Simulation is definitely very handy. In fact, okay, one of the grouper mechanism that I was showing, like where there's an input and output, it's actually a simulation. It's a FEM model. One other advantage component mechanism gives is FEM scheme can be readily used for component mechanism because there are no joints. Because modeling a joint is not that easy. Rigid linkages. So this one, as long as you have the design, you can directly put in the material properties, put the constraints, and you can solve in terms of FEM. Now once the FEM does its job, that's where we talk about the simulation. So once you have the simulation, then it is up to you to see whether it has satisfied the requirements that you are having. So in some sense, like the fatigue thing that you were talking about, if you see that at certain locations the beams are bending a lot more than what they should, or rather, it's not about bending, it's about the stress that is going into the beam. If it's a lot more than the yield strength of the material that you are proposed to use, then it doesn't make sense for us to use that material. Either you should make a change in the material or you should change the design, which will have a less stress coming onto that particular. So simulation definitely plays a big role. In fact, Kishore is one of your batchmates, so he's working on this kinetolastic static maps. So what we try to do with that particular thing is, have you heard about Moody's chapter? Fluid mechanics? Okay. What is a good point of fluid mechanics, which I liked when I was a BTech student? In fact, even when I went to IIC interview, I was always thinking I will talk about fluid mechanics. After looking at such large panel of people and a lot of fluid mechanics people, I said, okay, I like mechanisms. And the questions went with mechanisms. There was only one block, Professor Anand Suresh. I just survived. But okay, so sorry, this is a digression. So fluid mechanics has a lot of these numbers. Knudsen number, Reynolds number, everybody has one number. Because modeling is very difficult there. And when the modeling is difficult, you rely on some empirical relationship, and that's what gives rise to these non-dimensional numbers, which has that scalability. When I say scalability, when I can capture a lot of physics of the problem into one number, one index, the reverse is very useful for me in the sense, Reynolds number, when it is low or high, I can directly relate it to the turbulence or the fluid flow being laminar. So there is a direct connection. I don't need to see the flow before I talk to the Reynolds number, but with the Reynolds number I can talk to the flow. The reverse is what is very useful. And they have made a lot of advantages, a lot of advantages are sought with respect to these non-dimensional numbers that we see in fluid mechanics. But it's very difficult for us to think about a non-dimensional number in solid mechanics. Can you think of it? Okay, you can have it in your mind when you're reading the literature. You can see there are very few. I don't know much. So, going by that kind of a thing, what we are trying to do here is goes back to your simulation problem. So, can I keep some parameters of my design constant so that any change I make in my design without doing one more simulation, I can say whether it works or not works. That is possible. So, for example, I take the cantilever beam because it's easy for us to get an intuition. Can I write? I'll just give you a sense of what a non-dimensional number white is used to us. You can ask questions to be sure. So, it's a cantilever beam and I'm planing it. Now, if you look at what is the formula for stiffness? Displacement is PL cubed by 3A. I is BH square, BH cubed by 12. Okay, so given this is the formula. Now, in this cantilever beam, if you look at our stiffness matrix, so if I were to get the stiffness, I just need to do P by delta. Right? P by delta will give you the stiffness. That means 3EI by L cube is my stiffness. Now, if you have a network of these complement mechanisms, these cantilever beams, it will form a matrix. Say, some entries will be there in the matrix. Now, the Young's modulus is a constant parameter that is getting multiplied across all the units of your matrix. Assume. You have a knowledge of FEM? Some of you? Okay, just to give an idea, usually you will solve an equation K is equal to F. When K is your stiffness matrix, that's what I am talking about when I talk about the cantilever beam. Now, if you look at the stiffness matrix in any FEM simulation, Young's modulus is something which can come out of the matrix itself. So, it becomes a constant multiplier out of the matrix. Likewise, if I keep certain things like what we call as an aspect, a slenderness ratio, that means this L by B, B is my limit. If I keep that thing, because there is an L cube and there is an H cube. So I can take that thing, if I call H, L by H as a slenderness ratio, then the same equation now will look like 3E B then by S cube or 12 will be there. Something of that form. Now, the idea here is if I keep E constant and if I keep my S constant when I am doing any design change, that goes back to your point, then any variation of my width, I can capture it by if I had done enough number of simulations. I don't need to do any new simulation because I know now the intuition or even the mathematical form that as long as I keep my E constant and S constant, there is a constant multiplier that comes out of my stiffness matrix. And whatever modification that I do with my geometry only modifies it only modifies the terms that are there outside. That means if I were to change just something like this, I have stainless steel cantilever beam. Now I want how the same beam with the same geometric parameters which behave for a polymer. The only thing that has changed in our equation is the Young's modulus. The other way around is that for Young's modulus, that is for polymer having the Young's modulus for the polymer and Young's modulus for the steel, then E1 and E2 is where to write. If both these characteristics should be similar if I were to put a constraint, the only option that I have is now playing with the S. If I keep the S ratio as if S1 was for this one, stainless steel and SS, and S1 was the aspect ratio, the slenderness ratio, and S2 was for this one. Now I know if I choose S1 by S2 as a particular ratio of this two, I will get the same feature as this one. Because my matrix has only that term coming out. Rest of these are constant. So these kind of non-dimensionality helps in having simulations, giving a perspective of how the design changes can happen without doing any more modeling or simulation. So this is very much within the scope of the way the design proceeds.
The analysis part is okay, doing some FEM you can do it. The thing is, to check the mechanism, what tools would you use?
Tools meaning, give an example. Simulation. Simulation you can check with the FEM as long as you are taking care in terms of the material aspect.
The design part is okay. The analysis, okay.
The design has different approaches. The design has different approaches. One is the topology optimization that I was talking about. Then there is an intuition. And there are also other techniques where you can, it's called a building block approach. That means each block when you put what happens to the system, you can keep understanding. And you can build a complete compliant mechanism using that approach. So there are various design approaches for compliant mechanisms. So what I am talking about is after you design, how you modify any design further to attribute or to take into the constraints that come as a problem, part of your problem statement, is where you can do all these kind of tricks. But to design a compliant mechanism, there are approaches. That's what I was talking about now. Sorry? Machine? The mechanism? Okay, because I'm in a startup now, I can tell it is not very expensive. To give an example, we have this micro force sensor, what I was talking about, what goes on to the micro pipette, the glass needle. There is a MEMS-based device which costs you about 3 lakhs. And the 3 lakhs is only for the chip, the MEMS device, and the all electronics around it. Whereas this compliant mechanism will not even cost you more than 1,000 or 2,000 in terms of its manufacturing. There's a vast difference because the kind of approach that you have, the problem itself is different.
So now the backup procedure is right.